So now today we are going to discuss last topic of unit number 2, that is Norton amplifier. So Norton amplifier is some different kind of the operational amplifier. Before that we have studied about the operational amplifier 741, which works on the principle of differential amplifier. Basic operational amplifier IC 741 works on the principle of differential amplifier. That means there is the output voltage is directly proportional to the difference of the two input voltage. So that was the basic fundamental of IC 741. Now the Norton amplifier work on the principle of current differencing. In which principle? Principle of difference in current. Basic operational amplifier works on the principle of difference of voltage, but the Norton amplifier works on the principle of difference in current. This is the basic and fundamental difference in between Norton amplifier and the normal IC 741. So now today we are going to discuss what is the basic functionality of this Norton amplifier, what is the symbol of this Norton amplifier, and what would be the value of output voltage and output in case of inverting terminal of op-amp and non-inverting terminal of op-amp. So these are the topics which we are going to cover in today's lecture. So as I told you, this Norton amplifier works on the principle of difference in current, and that can be achieved with the help of current mirroring. So in which basic principle it works on the fundamental of difference in current? By the use of current mirror circuit. So due to this function, the difference of current instead of the voltage, these amplifier types of mainly referred to as a Norton amplifier. And one more thing is that why it's called as the Norton? Why? Because it works on the principle of current, as same as in case of the Norton's theorem. You know, now in case of the Norton's theorem, we works on the principle of current, where actually we calculate the value of Norton's current. So from there we take this particular naming of this amplifier as Norton amplifiers. So from there also you can relate this thing, that the Norton amplifier works on the principle of difference of current. What basic advantage of this Norton amplifier is its low cost. Its cost is very low. And second thing is it works on the principle of single polarity power supply. Basic operational amplifier can work in dual power supply, either single-ended or double-ended. So there are different kinds of the power supply that can be used in case of the IC 741. But suppose in some application you are having only single power supply, then how can you use particular circuit for any kind of the application? So if you are having some single polarity power supply, then on that condition you need to use only Norton's amplifier. Norton's amplifier is having a functionality to use it with the help of single polarity power supply. So this is a main application or the main thing you need to remember about the Norton's amplifier. It can work with single polarity power supply. And how it can achieve this single polarity power supply? With the help of LM3900. So LM3900 is basically a Norton amplifier, and today we are going to discuss everything related to this LM3900. So LM3900 is a most popular Norton's amplifier. Here in right hand side, you can see the symbol of the Norton's amplifier. It is the symbol of the Norton's amplifier, where at the inverting terminal, the value of current is minus II, and at the non-inverting terminal, the value of current is plus II. And in between, this represents that there is a difference of current. So differencing of current is to be denoted with the help of this symbol. So this is a symbol of the Norton's amplifier circuit. Now what is LM3900? So these are some characteristics of the LM3900. It is mainly useful when you are having only a single power supply is available, then you need to choose LM3900 in case of single power supply. What is the output voltage swing? In case of LM3900, output voltage swing is near ground and approximately equal to the diode drop in positive direction. So diode drop is how much? 0.7 volt. So there is a swing of 0.7 volt in the output. So how much swing can be achieved with the help of LM3900? 0.7 volt, or the drop across the positive direction of the diode. In experimental purpose, the power supply used by this is plus 12 volt. Plus 12 volt power supply is used in experimental purpose, but total range of the power supply on which this LM3900 can be used, so that range of the power supply is in between 4 volt to 36 volt. In between 4 volt to 36 volt, you can use this LM3900 without any kind of the problem. So there would not be any kind of the problem into the LM3900 when the range of the supply is in between 4 volt to 36 volt. Internally, in LM3900, 4 different operational amplifiers are connected, so that can be give a single power connection. Internally, there are 4 operational amplifiers inside this LM3900. So those 4 operational amplifier is not needed to give the different power supply. You can use the same set of power connection to them, but they are otherwise independent. So they works independently, but we can give the same set of power connection to them. Now, LM3900 is a 14-pin DIP package with 4 identical op-amps. As I told you, there are 4 identical op-amps inside the LM3900, each with having an inverting and non-inverting input terminals and 1 output terminal. So these 3 terminals are already present in case of LM3900. 2 are the input terminals and 1 is the output terminals. And these op-amps are very much different from the usual op-amp and must be used completely in a different way. And it is very much clear from the starting topic that it works on the principle of current differencing instead of the voltage differencing. That means the operation of these operational amplifiers are completely different from whatever we have studied in case of IC 741. So instead of differential amplifier, input stage is current differencing circuit. So this is the input stage of this LM3900, where you can see this arrangement is called as the current mirroring arrangement. Current mirroring. As already we have discussed about the current mirror circuit. What is current mirror? In case of the current mirroring, output current must be equal to the mirror image of the input current. That is the basic definition of the current mirror circuit. Here I plus is the input current to this transistor and I plus here is the output current. But due to that current mirroring circuit, this I plus must be equal to this collector terminal current. This collector terminal current must be equal to this input current. So due to that, and here the value of current is what? Here the value of current is I minus. Here the value of current is I plus. But due to current mirror, same current I plus will be generated over here. Please do consider over here. Na? Please left this thing. Okay. Suppose I am not concentrating on this I plus right now. We are having only these 2 terminals. At the output terminal of the Norton's amplifier, you are able to see only these terminals. Now, this inverting terminal and this one is non-inverting terminal of one. So when this is I minus is the input current at the inverting terminal, here the value of I plus at the non-inverting terminal, but internally or at the inside of this Norton's amplifier, this arrangement is what? Is a current mirroring circuit. And as per the current mirror, we know that the input current must be equal to the mirror image of the output current. This collector terminal is the output terminal. Na? So if it is I plus, so this will also be I plus. This IC must be equal to I plus. That means the part of this I minus will flow across this collector terminal. some part of this I minus will flow across the collector terminal of this transistor. That means how much would be the value of current over here? What will be the value of current? So current will be equal to I minus of I plus. How much would be the value of current? This I minus of this I plus. Why? Because that much part has been subtracted from that I minus current. Na? So this is actually the current difference. So here that would be much more clear. This is the complete internal circuitry. So actually I was discussing this part. Na? I was discussing about this particular part. You can see these two circuits are same. These two circuits are same. So if it is I plus, here the value of current is I minus, and some part of the I minus is across this transistor number 7. So when some part of the current is flow across the transistor number 7, so what is the value of current at the base terminal of Q6? So that will be I minus of I plus. So this is called as what? Current differencing. So I minus of the I plus, amount of the current will feed to the base terminal of transistor number 6. Transistor number 6. So as per this internal circuitry of the Norton's amplifier, it is basically divided into two sections. This internal circuitry is divided into two different sections, where first section is current differencing section. First section is what? First section is a current differencing section, and that consists of transistor number Q6, Q7 and D1. So this part is one first section of this Norton's amplifier. This is the first section of this Norton's amplifier, Q6, Q7 and D1, where Q7 and D1 is a current mirroring part, and Q6 is used to feed the difference current. Q6 is what? Q6 is used to feed the difference current. Now the output of this transistor number 6, will be used to feed the current at the gain stage of the transistor. So that much of the part is the second section of, this is the second section of the Norton's amplifier. So there are two sections. First section is current differencing section and second section is gain stage. So which part is used to provide the necessary gain in case of Norton's amplifier? So transistor number Q1 to Q5, this Q1, Q2, Q3, Q4 and Q5, all 5 transistors are used to produce the necessary gain in case of Norton's amplifier. As in case of normal IC 741, as we have discussed earlier now, in case of IC 741, the very first stage is a differential amplifier. The very first stage was what? Differential amplifier, which produces the difference of the input voltage. Similarly, here the first section is a current differencing amplifier, which produces the difference in current. Which section? Q6, Q7 and D1. Now as the intermediate stage in case of IC 741, which produces the necessary gain, here the transistor number Q1 to this Q5, these all the transistors are used to produce the necessary gain of the Norton's amplifier. So this is the complete circuit diagram of Norton's amplifier. So current differencing portion is what? That works on the principle of current mirror concept. Now D1 and Q7, that make up the current mirror, as we have discussed already now. Now the current flows down to D1 and mirror onto Q7. So everything we have discussed. So what is the basic fundamental? The first section is used as a current differencing. Current differencing is to be generated with the help of current mirroring. Second section is the gain stage. Gain stage is used to produce the necessary gain of the Norton's amplifier. Now this I minus I plus is feeds to the Q6, as I told you, then amplified by the following stages. These are the stages. Now, one more important thing related to the current is that here the value of current is what? Difference of the current is I minus of I plus. So when the value of I minus is greater than I plus, this I minus is greater than what? I plus. On that condition, output will be what? Output saturation will be low. So output will saturate low. When the output will saturate low, when the value of I minus current is greater than I plus current, that means inverting terminal current must be greater than non-inverting current. On that condition, the output will saturate low. But if I minus is less than I plus, inverting terminal current is less than non-inverting current, on that condition, output will saturate high. Please remember this thing related to the saturation of the output voltage in case of Norton's amplifier. It depends on the difference of the current or the current fed at the inverting and non-inverting terminal of the Norton's amplifier. Now the feedback element as usual is used to decrease the value of gain. It produces the small gain. Now the output is however a voltage as with the usual operational amplifier, and as I told you, Norton's refers to the Norton equivalent circuit for a current source. So this is all about the internal circuitry of the Norton's amplifier. Please remember all the things related to that. Then only on that condition you would be able to work with this Norton's amplifier. Now moving further, the working of this Norton's amplifier, how this works. Then we will discuss the inverting and non-inverting terminals of the operational amplifier. So the input impedance for the non-inverting input is little more than the dynamic resistance of D1. The non-inverting terminal impedance in case of Norton's amplifier is more than the dynamic resistance of D1. Which is D1? This is D1. So D1 resistance is less as compared to the non-inverting terminal resistance, and that can be calculated. This resistance is dependent on the input current and can be calculated with the help of this formula. That means 26 millivolt divided by I plus, where I plus is non-inverting terminal current. So with the help of this formula, you can easily calculate the value of how much is the impedance connected at the non-inverting terminal of the Norton's amplifier. Another important point is that both the inverting and non-inverting inputs are locked approximately one diode drop above ground. As I told you earlier that there is a difference of voltage is how much? Only drop across a diode. Only drop across a diode in positive direction. In positive direction. So how much is the difference in voltage? So at inverting and non-inverting inputs, these are locked by approximately one diode drop above ground. That means 0.7 volts. So that is the basic difference. So you may take it as 0 volt also. So in most of the calculation, we take as we do in case of the normal IC 741 that VA, if VB is connected to ground, so due to virtual short circuit, VA is also connected to ground and we take it as a 0 volt. Similarly, here we will also take it as a 0 volt. Why? Because as compared to 12 to 15 volt, the value of 0.7 volt is negligible. So in most of the calculation, please remember, if you will not be able to see there the virtual ground directly. So you may take it as a 0 volt. So this is important for solving the question related to the Norton's amplifier. So this can be beneficial for current summing node. That means related to the questions related to Norton's amplifier, but it requires that the some form of the input resistor be used if a voltage input is expected. Why? Because here only we are considering the current, but if we want to use some voltage, then it's compulsory to connect some resistance. Then only the voltage drop will be there. Now, if there would be some voltage drop, then only you can use that voltage for the experimental purpose. So whenever you are concentrating or whenever you are interested for the voltage, then you need to connect some amount of the input resistance. So in problems also we need to calculate how much amount of the resistance can be used for the proper operation of the circuit, or for a particular operation how much resistance can be connected. So these are related to some problem. A side benefit of this is that a large enough input resistance, there is virtually no limit to the input common mode voltage range, and potential will drop across this input resistance. And for proper AC operation, the appropriate biasing current must be used. For proper AC operation, what should be the criteria? We need to choose the biasing current, appropriate biasing current at the input. So we need to set the biasing current. Now, first kind of the Norton's amplifier, that is inverting Norton's amplifier. As I told you, there are 3 terminals in case of the Norton's amplifier. 2 are the input and 1 is the output. 2 input terminals are, one is inverting terminal and second one is non-inverting terminal, as usual in case of IC741, and output is taken as at the output terminal of Norton's amplifier. So as you can see over here, this is the connection diagram of the inverting Norton's amplifier, where this Ci and C0 are the coupling capacitor which is used to reduce the DC voltage. I think that would be remembered to you in case of the IC741, there is a direct coupling. So what was the disadvantage of the direct coupling is that when all the transistors are connected directly to each other, then AC as well as DC signal will be amplified inside the operational amplifier. So the operating point was changed in case of IC741. So there we need to use one extra terminal or one extra block that is called as the buffer or level shifting block. So the main use of that buffer or level shifting was that to reduce the amplified DC voltage to 0. But here in case of the Norton's amplifier, coupling capacitors are connected. So when coupling capacitors are connected, then we don't need to worry about the DC biasing. Why? Because this coupling capacitor completely blocks the DC voltage present into the circuit. So it can be very much beneficial for the AC amplifiers only, not for the DC biasing. So there is no any kind of the chances for amplification of DC level. So no need to take care about the operating point. So this is the benefit of the coupling capacitors used here in case of Norton's amplifier. So DC biasing level is no worry about this. The input and output coupling capacitor as well as RB, that serves to convert the bias voltage into the biasing current. And one important thing you need to remember in case of inverting Norton's amplifier, the bias is set by the current I plus. How to set the biasing current? As we told you that we need to set the biasing current for the proper AC operation of the Norton's amplifier. Either we are using the inverting Norton's amplifier or we are using the non-inverting Norton's amplifier. We need to set the biasing. So in case of inverting Norton's amplifier, how to set this biasing? With the help of current I plus, not by the voltage divider. Remember this. In case of the inverting Norton's amplifier, how to set biasing? Biasing is to be set with the help of current I plus, not by voltage divider, as it would be in case of usual op-amp. So whenever you are using inverting, set with the help of I plus current. Now this is the calculation for the voltage gain in case of inverting Norton's amplifier. So it's an internal circuitry at the input terminal of the Norton's amplifier, where this is your output terminal. Total amount of the current from output to the input with the help of feedback resistance is I plus base current IB, that will be at the inverting terminal of the Norton's amplifier. This is the inverting terminal I minus, and this is the non-inverting terminal I plus, and this part is the internal part of the Norton's amplifier. So here, what is the value of output? So output will be diode drop. It is VD. VD is the voltage drop across the diode. So what is the value of output? This diode voltage drop, VD, minus plus drop across this resistance RF. So if we add these two voltages, then only on that condition we can calculate the value of output. So output will be what? Output is equal to VD minus this VD minus plus drop across this RF. RF is what? RF multiplied by current. Current is I plus IB. So that is the value of I. That is the value of output voltage. And what is the value of current? What will be the value of current? I plus. So I plus is non-inverting terminal current. Where is I plus? I plus is at the non-inverting terminal of the Norton's amplifier. So here the value of voltage is V plus. Here we are taking it as VCC. Let's suppose this V plus is VCC voltage. What is this terminal voltage? This is the voltage across the diode. This is the voltage across the diode at the positive terminal of the diode. So what is the value of current? I plus? I plus will be supply voltage minus diode voltage divided by RB. Supply voltage minus diode drop divided by RB. That is the value of current I plus. Now substitute this I plus over here in equation number 1. When we substitute this here, so this is the value of output. Output is equal to VD minus plus RF. This is the value of I plus. V supply minus VD plus divided by RB plus IB. Now supply voltage is approximately 12 volt, as I told you in case of the Norton's amplifier. When we are using it for the experimental purpose, the value of supply voltage is what? How much? Plus 12 volt. And what is the value of diode voltage? Diode voltage is equal to 0.7 volt. So 0.7 volt is much lesser as compared to the supply voltage. So here we may neglect the value of the supply voltage. So when we neglect the value of the supply voltage, so and also the value of IB is relatively small. The value of IB is relatively small. Then what is the value of output? So output will be equal to how much? V supply. V supply multiplied by this RF divided by RB. Output will be V supply into RF divided by RB. Or at a midpoint, at the center point, what will be the value of RB? RB is taken as twice of RF. Remember this. At the center, the value of RB is equal to twice of RF. And from there, what is the value of gain? Gain is equal to minus of RF divided by RI. So this is the value of gain in case of inverting Norton's amplifier. In case of inverting Norton's amplifier, remember how to calculate the value of RB. RB is non-inverting terminal resistance. RB is what? Non-inverting terminal resistance, and the value of that resistance is twice of RF. That means twice of the feedback resistance. And how to calculate the value of gain? Gain is equal to minus of RF divided by RI. So this is the value of gain and input resistance. Now, one question related to this inverting Norton's amplifier. This question is same as the calculation we have done over here. This question is related to this part only. So as per this question, using the LM3900, we need to design an amplifier. Here it is mentioned that you need to use LM3900. That means we are talking about the Norton's amplifier. So design an amplifier that operates from a single plus 9 volt battery, has an inverting voltage gain. That means we are talking about the inverting Norton's amplifier. Voltage gain is how much? 20. Input impedance of at least 50K and lower break frequency should not be more than 100 Hertz. Then for that we need to design an inverting Norton's amplifier. So this is the solution of this question. So what I told you, how to calculate the value of gain. Gain is equal to minus RF by RA. From there, what will be the value of RF? So first, one thing you need to remember, we need to design the value of amplifier. Design, that means we need to design this circuit. We need to design this circuit. And this circuit, what are the unknown parameters? First, make a picture what you want to calculate. So in the case of the inverting Norton's amplifier, you need to calculate the value of resistance RF. You need to calculate the value of resistance RB. These are the unknown parameter, and one parameter is coupling capacitor. So these three parameters you need to calculate over here. Then use the formula. By which formula you may calculate these values. So first formula you have the formula for the voltage gain. Also you have the formula for calculation of RB. So these are the two things you have. Then how to calculate the value of this RF? Why? Because RB is dependent on RF, and also you need to calculate the value of RF. The value of RF is not given. Now only input resistance is given. In question RI is given. In question AV is given, and in question frequency is given, and also the supply voltage Vin is given. So these are the voltages only given to you. Then by this voltage gain formula, the value of AV is given to you, RI is given to you. So from there you can easily calculate the value of RF. So what is the value of RF? RF is equal to minus of AV into RI. Then RF is equal to minus 20. It's given as 20, but it is what? It's a non-inverting voltage gain. Na? So in case of inverting or non-inverting, in each and every condition, the value of gain is positive. Resistance will also be positive. So no need to minus and minus. You may take it as a positive also, or you may take it minus. But in each and every condition, the value of resistance would be positive only. So RF is equal to 20 multiplied by input resistance is given as 50. So from there, RF is 1 mega ohm. Now RB is what? RB is twice of RF. So 2 into 1 mega, that will be equal to 2 mega. Very easy, na? Only with the help of two formulas you have calculated these parameters. Now third one is the coupling capacitor. So coupling capacitor depends on the break frequency. Already many times we have discussed about, in case of the coupling capacitor, how to calculate the value of break frequency. So break frequency is equal to 1 by 2 pi RC. Break frequency is what? 1 by 2 pi RC. Now FC is given. FC is given. Already the value of resistance is given. Resistance is here as input resistance. Then you may easily calculate the value of C. C will be equal to 1 by 2 pi R into FC. After substituting this will be the value of final capacitance. So this is a way by which you may easily calculate the various parameters, or you may easily design the Norton's amplifier. Only you need to remember what the things is given in the question and what you want to calculate. First of all, make the picture, then do one by one as per the requirements. So I hope that question and whatever we have completed, that would be clear to all of you. Now moving further, this is one more calculation related to the inverting amplifier based on this simple. If the value of, suppose the value of, you need to calculate the value of voltage gain. That much part we have calculated over here. If the value of supply voltage is given over here, then you may also calculate the value of output with the help of this formula also. This is a simple basic method. It is not dependent on any kind of the break frequency, any kind of the input impedance. It's a simple calculation of inverting Norton's amplifier. How to calculate this? Let here the value of current is I1. IN is the Norton's current at the inverting terminal. Here the value of current is IP, where P is for positive terminal, N is for negative terminal. IF is the feedback current. Now apply KCL at this inverting terminal here. Apply KCL over here. So IF is equal to I1 minus IN. IF is equal to what? I1 minus IN. But due to current measuring, what? IN is equal to IP. Why? Because due to current difference, I told you both the terminals are connected to each other. So IN is equal to IP. Let's substitute the value of IN is equal to IP. Why I am calculating in place of IN, we are calculating IP. Why? Because we need to take this resistance will also be in consideration. Na? That's why I am replacing here the value of IN by IP. So IF is equal to I1 minus IP. Then what is I1? What is I1? I1 is the current across this 10 kilo ohm resistance, where we have represented this resistance in terms of R1. So IF is what? I1 is what? Vin divided by R1. Why not we are considering this terminal voltage? Before that, already I told you, in case of the current difference in how much is the voltage drop in inverting and non-inverting terminals of Norton's amplifier, there is voltage difference of only one diode drop. That means 0.7 volt, and that can be taken as 0 volt. That's why this terminal voltage is 0. So I1 is equal to V1 by R1. And what is IP? IP is, this terminal is VCC. So VCC divided by this resistance RB. So VCC divided by RB. So that is the value of IF. Now what is V0? V0 is equal to IF into RF. V0 is equal to IF into RF. So V0 is minus IF into RF. So substitute the value of IF from here to there. So this is the final value of output voltage. So this is one more method for the calculation of output voltage when we are not considering the capacitance, internal impedance. So by this also you may calculate the value of output of Norton's amplifier. Now last topic is non-inverting Norton's amplifier. So in case of inverting Norton's amplifier, how the biasing is to be given? With the help of I plus. Just consider the difference in between inverting and non-inverting Norton's amplifier. This is the main difference in between inverting and non-inverting Norton's amplifier. How to give the biasing to these two circuits. In case of inverting Norton's amplifier, we give the biasing with the help of I plus current. With the help of I plus current, but not with the help of voltage divider circuit. But here, in case of non-inverting Norton's amplifier, we give the biasing with the help of voltage divider circuit. It's confusing now. So please remember this thing. In case of inverting, biasing is to be given with the help of I plus current. But in case of non-inverting, biasing is to be given with the help of voltage divider circuit. So this is a basic difference in inverting and non-inverting Norton's amplifier. Now calculate the voltage gain in case of non-inverting Norton's amplifier. So here the value of, at first, the input resistance is Ri, and at the non-inverting terminal, let the value of input impedance is denoted as Zin plus. So what is the value of Zin? Zin is equal to Ri plus this Zin plus. Let this impedance is Zin plus. So that is the value of total impedance connected at the non-inverting terminal of the Norton's amplifier. Now due to virtual ground, these two terminals are connected to each other. So V output is equal to what? Total voltage drop across this resistance. Let this voltage drop across this resistance is VRF. So V output is what? RF into I minus. Why? Because here the value of current is what? Here the value of current is I minus. So I minus into RF, that is equal to V output. This is the flow of the current. Yeah. Now V in drops across this. Now what is the value of V in? V in voltage will be equal to current. What is the value of current at non-inverting? At non-inverting terminal, the value of current is I plus. At non-inverting terminal of Norton's amplifier, the value of current is I plus. So I plus multiplied by this impedance, that will be equal to the voltage. So I plus multiplied by this Zin. Zin is equal to, already we have calculated here in equation number 1, Zin is equal to Ri plus Zin plus. So that is the value of total input voltage. Now what is gain? Gain is equal to output divided by input. Already we have calculated the value of output. Already we have calculated the value of input. Just take the ratio of these two. So that is the value of AV. So AV is equal to RF I minus divided by I plus Ri plus Zin plus. Now these two currents are equivalent. So we may cancel it out. So AV will be equal to RF divided by Ri plus Zin plus. So this is the value of gain of non-inverting Norton's amplifier. This is the value of gain in case of non-inverting Norton's amplifier. And one more calculation for the output voltage of Norton's amplifier. So here the value of current is IP. IP is positive terminal current. So IP is equal to what? This current is I1. This terminal current is I2. So IP is equal to I1 plus I2. What is this IF? Feedback current is what? Feedback current is nothing but this IP current. Why? Because the same IP current is flowing across the feedback terminal. So IF is equal to IP. So from there, IF will be what? I1 plus I2. What is I1? I1 is voltage drop across this resistance. That means V in divided by R1. what is I2? I2 is voltage drop across these resistors. So here let the voltage is VCC. So VCC divided by RB. RB is what? These equivalent resistance is called as RB. With all the equivalent resistance is here denoted as RB. So IF is equal to Vin divided by R1. Now VCC divided by RB. And what is V0? V0 is equal to IF into RF. What will be the whatever will be the voltage drop across this feedback resistance, that will be your output. So V0 is equal to IF into RF. Substitute the value of IF from here to there. So that is the final value of output. So this is the final value of output. What is the basic difference in the output of non-inverting and inverting terminal? Here all the voltages are same. It's also plus, but in case of here input voltage is negative. Why? So because in case of inverting Norton's amplifier, there is a phase shift of 180 degree in between input and output, and in case of non-inverting, there is a phase shift of 0 degree. So simple. Already many times we have discussed this thing. That's why there the sign was negative. Here the sign is positive in case of input signal only. Now the last thing of the points to remember in case of Norton's amplifier, the input are current sensing and thus require some form of input current limiting resistance. Here in case of Norton's amplifier, whenever you are going to design Norton's amplifier, in each and every condition you need to require some form of input current limiting resistance. Then you move further for the calculation. Second thing is, as with an ordinary op-amp, voltage gain is set by the two feedback resistors here in Norton's. And third one is a DC bias potential must be fed into the non-inverting terminal via current limiting resistance RB. So in each and every condition, DC supply voltage VCC must be fed at the non-inverting terminal, not at the inverting terminal of Norton's amplifier. In each and every condition, VCC must be connected at non-inverting terminal only. And this resistor is normally twice the size of RF. So what is this RB? That's why we have written over there, na? RB is equal to twice of RF. So this thing should be remembered. What is the value of RB? RB must be equal to twice of RF. So if you remember these some concept related to the Norton's amplifier, you may easily work with the Norton's amplifier. So this is all about the Norton's amplifier. Now we have completed unit number 2, and the related quiz related to this last topic of unit number 2, I will distribute that the link for the quiz at 1 o'clock after the completion of lecture number 3, as same as the previous lecture. So thank you so much for today. If you have any kind of the doubt, you can drop a message related to that. Thank you so much.
Thank you, sir.